Okay, we left off looking at question 15.57. And what we want to do now is see if we can put these pieces together to make a structure that makes some sense. So let's see if we can do that. We have an isopropyl group. So we have this isopropyl group here. Then we have a carbonyl, and we have a methyl group. And really, there's only one way to put that together. So the only way that we could put those pieces together, I'm just going to redraw it here, would be to make a ketone where we have our carbonyl like this. We have the methyl group on one side, and then we have the isopropyl group on the other side. Now let's ask ourselves, does this make sense? And the first thing we're going to do is we're going to estimate the chemical shift of this methyl. We know that the baseline of a methyl is 0.9 parts per million. However, it's alpha to the carbonyl of a ketone, so we add 1 and we get 1.9 parts per million, and that would be a singlet that integrates for 3 protons. So it makes sense that it would be this methyl group. So that seems reasonable. Then if we look at the methine, this one right here, we know that the baseline for a methine is 1.7, and that is alpha to the carbonyl. So we add 1 to that, and we end up with 2.7 parts per million. And we have an integration of 1, so it's 1 proton, but it's coupled next to 6 protons, so we would have a septet that integrates for 1 proton. And so that would be the signal at 2.58. Again, it's not exactly at 2.58, but it's very close to 2.5. So it will certainly suffice. Then the other part of the isopropyl group are the 2 methyl groups. So for the 2 methyl groups on the end, I'll get my blue pen here. So this one and this one, their chemical shift, the baseline, again, is 0.9 parts per million. We're going to add 1/5 of 1, which is 0.2. So that gives us a chemical shift of 1.1 parts per million. And we have a doublet that integrates for 6 hydrogens. So that is going to be these protons. And you can see the chemical shift is very accurate in this case. And so this structure that I have written here in black ink is consistent with the data that we were provided. Is everybody with me on that? And can I get a thumbs up on that one? Any questions about that one before we move on and try the next one? All right, great. Let's give the next one the old college try. Let me just maybe move this out of the way here. It's kind of in the way. There we go. Like that. So let's take a look at the next one, B. We have our molecular formula, C5H12O. That means we have an HDI that is 0. We have no double bonds. We have a triplet at 0.91. Now the baseline of a methyl is 0.9. We have nothing below that, so this must be a CH3. So it must be a methyl. And if it's a triplet, that means it's coupled next to 2 protons, right? Because we use the N+1 rule. 2 + 1 gives you 3. So we must have an ethyl group in here. And if you look over here, we have at 1.50, we have 2 protons that integrate for 3. Or sorry, 2 protons that give you a quartet. So that must be these 2 protons. So these are the ones at 0.91. These are the ones at 1.50 parts per million. And it's a quartet because 3 + 1, the N+1 rule. So that means we have an ethyl group, and we've taken care of these 2 signals. Next, we have a singlet that integrates for 6 protons. So it's at 1.19. So that means that we've got 2, that would probably be 2 methyl groups that are chemically equivalent. So we'll put here CH3 times 2. And again, it's a singlet. It's not coupled next to any protons. And then the last one at 2.24 is 1 hydrogen that is a singlet. Now, if we look at this molecular formula, we have C5H12O O, we have an HDI of 0. So that means the only possible functional groups that we could have are either an ether or an alcohol. Is this an ether or an alcohol? Well, let's count up the number of carbons. We have 1, 2, 3, 4. We need a fifth carbon. So we need to have a fifth carbon somehow. And we also have a hydrogen that is a singlet. So this could possibly be a hydrogen of an alcohol, right? Because we know that an alcohol hydrogen will have a chemical shift between 2 and 5 parts per million. So that might be that. And if it was that, then that would mean that we have a quaternary carbon in here somewhere. That means that we would have a carbon that has no hydrogens attached to it. Now, could we put all these pieces together to come up with a structure that seems reasonable? Well, if we think about it, we have our ethyl group. So we have our ethyl group like this. Okay. Then if we took our quaternary carbon and we attach 1, 2, 3, 4 things to it, one of them could be the hydroxyl, and the other two could be the two methyls, like this. So then, if we write down our letters, A, B, C, and D, this would be my A, or these would be my A protons. These would be my B protons. These would be my C protons, and this would be my D proton, just like that. And now we have a structure that is consistent with the data. Did anybody get that one or get something similar to that? Yeah. The way that I decided on the quaternary carbon was basically by process of elimination. So I knew that I had a methyl, a methylene, and then 2 more methyls. So I had all of this. I had the methyl, the methylene, and I had these 2 methyls. And then I knew that I had 1 hydrogen. Okay, I had 1 hydrogen in the molecule somewhere. So I chose to put that hydrogen in an alcohol. And then I said, okay, well, if I do that, the only possible way I can have these connected together would be to have a quaternary carbon. It's the only option. I mean, other things that you could try would be if you did something like this, CH3, CH2, and if you made an ether like this, CH, and then you have, I don't know, if you had something like this, this is 1, 2, 3 methyl groups, okay? It's a methylene, it's a methyne, and, you know, it's consistent with, you know, the carbons and everything, but the problem is would be the splitting here, Katie. So if you look at this methyne, for example, it's coupled next to 1, 2, 3, 4, 5, so that would give you a sextet. Don't tell me that all got deleted. It did. Anyhow, so you would have a sextet somewhere in the molecule. But did that make some sense, Katie? What I just said? Sorry, I'll try to write that down. Okay, cool. Yeah. So, you know, I'd kind of run through my mind some other options. But again, if we have this, okay, like this is the only possible structure. Right, so let's go back here and label this again, A, B, C, D. So this is my A protons, these are my B protons, these are my C protons, and my D proton, like that. Okay, great. Let's try the last one. So let's zoom in here on this one. C4H10O, we have an HDI, which is equal to 0, no double bonds, no rings. We have A, B, C, D. Our A protons, we have 6 hydrogens that give you a doublet. So where else did we ever see 6 hydrogens that gave us a doublet? Well, that was normally when we had an isopropyl group like this, okay? That's the only time we've seen that before, but let's just have that in our mind. The next thing is we have 1 hydrogen that's a multiplet. So yeah, okay, we have 1 hydrogen that's a multiplet. And if we have next, we have two hydrogens that are a doublet, that means that if we had two hydrogens here like this, and I'll just make this in red here, okay? If we had something like this, that would make sense because these two hydrogens are split by 1. That would give you 1 plus 2, or 1 plus 1, which gives you 2, a doublet. Then you'd have this methine is split by 1, 2, 3, 4, 5, 6, 7, 8. That would give you a nonette. There's no such thing as a nonette. Okay, it's just too many peaks. They're going to start to overlap. So this would give you a multiplet. Multiplet. All right. Whereas this one would give you a doublet. And these ones are coupled next to one proton. So all of these would also give you a doublet. Like that. So that is consistent with what we've got here. And then if we have an HDI of 0 and we have a hydrogen at 3.92 that's a singlet, that's probably an alcohol. And I've actually kind of figured out the structure already. So now our structure would look something like this, where we have something that's like an isopropyl, but this is actually an isobutyl group. So this would be the structure of our compound. This would be the D proton. These would be the A protons. This would be the B proton, and these would be the C protons. So we end up with this compound, which is called isobutyl alcohol. Any questions about that one? Following the same kind of rationale, just slowly kind of piecing it together. All right, let's take a look at another one. So let's take a gander at this one here, 15.59. So 15.59 asks us to deduce the structure of a compound with this molecular formula that produces the following NMR and carbon-13 spectrum. We might have to zoom in on this one a little bit to see if we can figure everything out here. But first question, what's the HDI of this compound? Did anybody calculate the HDI? So if you have C9, H10O2, HDI is equal to, could anybody answer that one? Remember, if you need to use the formula, so HDI is equal to 1/2, 2 times the number of carbons, plus 2, plus the number of nitrogens, subtract the number of hydrogens, and the number of halogens. Did anybody get a number here? Okay, so our HDI would be 5 for this compound. So we have an HDI that's, thanks, Kiana. Absolutely, we have an HDI that's equal to 5. Okay, 5. That's a lot of unsaturation, but what do you think it means if we have 5 protons and around 7 parts per million? You zoom in here and you see this is 7.123. So this is around 7.3 parts per million. What kind of protons do you think these are if we have 5 protons at 7 parts per million? If we have protons that are in between 6.5, so from here to here, what kind of protons are those going to be? Exactly. They are aromatic. Aromatic. So that means if you have 5 aromatic protons, there's a good chance that you have an aromatic ring in the molecule. And if there's 5 aromatic protons, that suggests that there's only one thing attached to the aromatic ring. Now, I have another thing to show you. Up here at around 12 parts per million, or very close to it, you can see it's just below. We have a broad, very broad singlet that integrates for 1 proton. Could anybody tell me what it means if I have 1 proton with a chemical shift of almost 12? We'll say it's very close to 12. What's the only thing that we would ever see that's up at 12? You might have to go back to the table to look at it. If you go back to the table that's in the lecture slides, Exactly. So it would be table 15.2. Table 15.2. My students are 100% correct. That means that we have a carboxylic acid. So we have a carboxyl group, and this proton, this broad singlet, is the acidic proton. Now we've taken care of all the HDI units because an aromatic ring has an HDI of 4 and a carboxylic acid has an HDI of 1. So we know that in this molecule, we have an aromatic ring and we have a carboxyl group somewhere. So now, if you count up all the carbons, we've taken care of 1, 2, 3, 4, 5, 6, 7, but there's a total of 9. So we're missing 2 carbons. We're going to have 2 more carbons. Now, if we look down here at the bottom end of the spectrum, it's kind of hard to tell, but this is a triplet that integrates for 2 protons, and this is a triplet that integrates for 2 protons. How can you have 2 protons and 2 protons that both integrate for a triplet? What would we have to have? The only way that you could have that is if you have 2 methylenes concurrently or successively, and they're attached to 2 different things, X and Y, because these 2 protons are going to be split by these 2, so you see a triplet, and then these 2 protons are going to be split by those 2, so you see a triplet. You would get a triplet and another triplet. Well, that works out because that gives us 2 more carbons and 4 more hydrogens. Now we've taken care of all the hydrogens. Let's count them up. In our aromatic ring, we have 5 hydrogens. Here we have a total of 4 hydrogens. And here we have 1 hydrogen. 5 plus 4 plus 1 gives us 10. Now we've taken care of everything just by looking at the Proton Nmr spectrum. We didn't even have to look at the carbon yet. And we've basically figured out the entire structure of the molecule. What we're going to do is we're going to take those 2 methylenes and we're going to connect them to the aromatic ring. 2 methylenes. And then we're going to put our carboxyl group on the end, like that. Just move that number 7. There we go. Like that. And there is the structure of our compound. To do a proper annotation, we're going to label the signals A, B, C, and D. This would be my D signal for my carboxylic acid. All of these, I'm just going to write C next to them because these are my aromatic protons. And these are going to be B and A. Now, what do you think is more electron withdrawing? What do you think is going to cause a greater de-shielding effect? A carboxyl group or an aromatic ring? And think, remember, there are no trick questions in organic chemistry. What do you think would be more electron withdrawing? The carboxyl, that carbonyl group, or an aromatic ring? Based on what you've learned in organic chemistry. Exactly. So, right, Nicole, it's going to be the carboxylic acid. And so this one is more de-shielded. So this is the one that's going to be closer to the carbonyl group of the carboxylic acid, closer to carbonyl. So this must be B, and these would be A, just like that. Now, we still haven't even looked at the carbon. I think we should do that. So I'm going to redraw the structure right here, just so we can kind of have it in our mind's eye. So we'll redraw the structure. I'll just draw the bond line structure this time. There we go. You can see that we have a total of, we have A, B. Zoom in here. We've got C, we've got D, we've got E, we've got F, and we've got G. So that means we've got a total of 1, 2, 3, 4, 5, 6, 7 unique types of carbons. But remember that there's free rotation around this bond. And so we have this carbon in the aromatic ring, but these 2 carbons are chemically equivalent. These 2 carbons are chemically equivalent. And then this carbon is unique. Of course, we have other unique carbons, this one here, and then this one here. Could anybody tell me which one is G, the one that's the most deshielded, and it's not a trick question? Where would I find G? Which one would be the G carbon? Anybody have a guess? Not a guess, but an educated guess. This one's all the way up around 180. So if we have something that's above, above 180, that means this is going to be the one by the carbonyl. Okay, so this is going to be G here. Then which ones are going to be the least deshielded? It's going to be B and A. Those are all the way down around 30. The one that's the most deshielded is B. That's going to be the carbon that's next to the carbonyl. A is going to be this one. And then we just have F, and we have the other carbons in the aromatic ring. So let's see here. Let me just remove these here. Just as kind of an aside, when you have something like F where it's really small, you see how it's a very short peak height? Oftentimes that can mean it's got no hydrogens attached to it. So I would say that F is going to be this one here. And C is also really small. It's only got one hydrogen attached to it. And then we have D and E. You can see that those both represent 2 carbons. They're about double the height. Now, it's not integration, but since they're so tall, they're producing a stronger signal. Why? Because there's double the amount of carbons, because they're chemically equivalent. Now, E is the more deshielded of the two. And so I'm going to pick E as being these ones here that are closer to the carboxyl group. And I'm going to pick D as being these ones that are more shielded. They're not as close to the carboxyl group. And there we go. We've annotated both the proton. Oops, can't really zoom out. We've annotated both the proton and the carbon NMR spectra for these 2 molecules. Any questions about that one? About 15.59. Because if not, we're going to move on and we're going to take a look at a combined spectroscopy problem. So let's do that. Just scooch ahead here. And we're going to take a look at a problem where it says deduce the structure of a compound with a molecular formula of C6H14O2 that exhibits the following IR. So they gave us an IR. They gave us a proton and a carbon-13. So we have a lot of information provided to us in this one. Well, the first thing I notice is that if the formula is C6H14O2, we have an HDI that is equal to 0. So we have no double bonds, no rings in this molecule. My question to you is, could anybody identify a functional group, excuse me, in the infrared spectrum? Is there a functional group that you recognize? Absolutely. Somebody said an alcohol. A few people did. Yeah, you're 100% correct, right? We know that we have the OH stretch. Therefore, this is an alcohol of some sort. All right. Other little things I notice is that, it's not aromatic. There's definitely no aromatic stretching, so not aromatic. I mean, it couldn't be because it's got an HDI of 0 anyway. But the thing is, we have 2 oxygens in here. If it's not aromatic, we don't have a carbonyl, so no carbonyl, or let's put here, no carbonyl in the molecule. There's no stretching around 1700, nothing, so it can't be a ketone or anything, and it couldn't be anyway. But there's 2 oxygens. Does that mean that there's 2 alcohols in here? Not necessarily. Could anybody tell me what's the other functional group besides an alcohol that I could have when you have an oxygen and there's no double bonds in the molecule? So there's one other type of functional group where we have an oxygen that's sp3 hybridized, no double bonds. Exactly. So either we've got 2 alcohols, but could there be an ether? Well, where do you see the carbon-oxygen stretching for an ether? We see it between 1,000 and 1,300. Well, looky. That's actually some of the strongest signals in the entire spectrum is these 2 stretches here. So this is going to be a carbon-oxygen stretch. So that suggests to me that we have an alcohol and an ether, two functional groups in the same compound, both an alcohol and an ether. Well, let's go in here in the Proton NMR. And the first thing I noticed is that if I have an alcohol, the first thing that my eye was drawn to was this. There's only one signal in here that it has an integration of 1. So this must be the alcohol. Okay, that's got to come from an alcohol. The other ones are kind of interesting because you really got to zoom in here, but you can see that this is a triplet. So this is a triplet. These ones here, I mean, this one looks like 1, 2, 3, 4, 5. So let's see, 1, 2, 3, 4, 5. It's hard to tell if there's something here or not. I can't tell if it's overlapping with the other signal. And then here it looks like you got 1, 2, 3, 4, 5, 6. 1, 2, no, 1, 2, 3, 4, 5. So that kind of looks like 5 as well. Again, it's hard to tell what's going on right here. I'm going to write quintet by this one. Quintet here. And then this one, I can't tell if it's a quintet or a sextet. I'm not 100% sure. So we'll put here sextet or quintet, maybe. Not 100% sure. And then if we go down here at the end, we have a triplet, and it's kind of hard to tell what's going on here. We definitely have a triplet here, triplet. And then here, it's hard to tell if these are triplets or doublets because it kind of looks like something is overlapping here. So we could put here triplet, triplet slash doublet. Not 100% sure. So let's go over and look at the carbon. And in the carbon, we have 1, 2, 3, 4, 5, 6 types of carbons. And we have a total of 6 carbons in the compound. So there we go. So really, we have nothing more than a bunch of carbons. You can see that they all have chemical shifts below 4. So in the proton, they all have chemical shifts below 80 in the carbon. And so, yeah, it would make sense that we have 3 carbons, that are attached to oxygens. These must be carbons that are attached to oxygen since they're so de-shielded. And then these are carbons that are not attached to oxygen. So these would either be methyls or, a carbon attached to another carbon. That's really the only possibility that we have here. So how are we going to put this all together? Let's see. Well, we've got a triplet. We've got another triplet. We've got a quintet. We've got a what looks like a sextet to me. I'm not 100% sure, but let's start with the protons that are really the most shielded, right? Because those are going to be the ones that are the farthest away from an oxygen. And what I'm thinking is if we put a bunch of carbons in a row, like this, CH3, CH2, like this first one would give us a triplet, and this one would give us a sextet, right? Because it's coupled next to a total of 1, 2, 3, 4, 5 protons. So that covers the triplet and the sextet. And then if we wanted to have a quintet, then you'd have to put another carbon next to it like this. And then this one would give you a quintet because it's coupled next to 1, 2, 3, 4 hydrogens. 4 plus 1 gives you a quintet. And then if you put an oxygen here, you would get another triplet. I'm going to put this one in blue. And that triplet, its chemical shift would be the baseline for the methylene is 1.2, but it's next to an oxygen of an alcohol. So we're going to add 2.5 to that. So that would give you something around 3.7 parts per million. So that makes sense that you would end up with a triplet that is that de-shielded. So I'm thinking that you've got a butyl group with an oxygen, and that takes care of all of these protons. So 1, 2, so it takes care of this one, and it takes care of one of these things in here. So let's just put a check mark by this. So what's left over, the only thing left over are 2 more signals that are multiplets that integrate for 2 protons. Well, how would you have that? Remember, I showed you earlier today, the way that you would get that would be to have 2 methylines attached to 2 different things, X and Y. So we could put those here. We could have a CH2 and another CH2 like that. That would take care of these protons and these protons. And then we still need to have our alcohol. So we could put that over here like that. Again, we would have another triplet here and another triplet here. And that takes care of everything in the molecule. So that means that all those signals up here, these must all be triplets. So there's no doublet in here, okay? Everything in here is a triplet. And that gives us the structure of our compound. We have our ether. Oops, I didn't mean to do that. We have our ether here, and we have our alcohol over here. So just kind of piecing it together slowly, methodically, I was able to rationalize my way through this and come up with something that is consistent with the IR spectrum, with the proton, and with the carbon-13 NMR spectrum as well. Not easy to do. It's definitely a puzzle that you have to piece together bit by bit until you get it. But let's try one more, and then we'll take another break, and I'll show you some other practice problems that I have that you could take a look at. All right, so it says 15.64, deduce the structure of a compound with this molecular formula that it exhibits the following IR, proton, and carbon NMR. So first thing I notice is that there's definitely no alcohol and no carboxylic acid in here. And you can scribble that down if you want. So no alcohol or carboxylic acid. That's for darn sure. Another thing is that there's no carbonyl. So if this is 15, 16, 17, there's no stretching around here. So no, we'll put here no. We'll just draw a carbonyl like this. But we do see some overtones here. Those are aromatic overtones. And remember that I told you the aromatic stretching was 2 to 3 signals between 1475 and 1600. And you can see that we have carbon-carbon aromatic stretching right here, aromatic stretching. So this must be an aromatic compound, and I'm sure you guys are faster than me, and you've probably already identified that C8H10O has an HDI that's equal to 4. We have an HDI of 4, so therefore that takes care of all of the aromatic rings. So we have an aromatic compound, and we've got an oxygen in there, but we don't have an alcohol. We don't have any other double bonds. So therefore, that means that this stretch, like we said in the last problem, between 1,000 and 1,300, this stretch here must be a carbon-oxygen stretch from an ether. So that means that we have an aromatic and we have an ether in the same compound. So now we've taken care of 6 of the carbons, gotten rid of C6, and we have also gotten rid of the oxygen like that. Now we have 2 carbons and some hydrogen. So let's take a look at our Proton Nmr spectrum. In the Proton Nmr, we have a singlet that integrates for 3, another one that integrates for 3, and we have a doublet of doublets, or 2 doublets over here in the aromatic region. Well, this is something that I haven't told you yet, but I want everybody to be fully aware of this. Whenever you see a pair of doublets in the aromatic region and they're kind of leaning in towards each other, like this, you have one going like this and one going like that, what that means is that you've got an aromatic ring that's got 2 substituents, 2 different substituents on the opposite ends, X and Y. So if we go over here, we know that we have an aromatic ring that's got something on here and something on here, okay? This is called para-substitution. That's the name of it. It's called para-substitution. All right, so we've got that. That takes care of 4 of the hydrogen, so that means we've got 6, so we've got 3 and 3. Well, what's the only possible way that we could put these together? We have one methyl that is not very deshielded. It's a little bit deshielded based on diamagnetic anisotropy because it's attached to an aromatic ring. But then, let me just maybe write it up here. But then we have another methyl group that's going to be very deshielded. That's all the way up around 4. Well, what would deshield it that far? It would have to be the ether. So we have our oxygen and our other methyl group here. And there, just like that, we've deduced the structure of this compound without even looking at the carbon. If we annotate it, we have proton A, B, C, and D. These would be the A protons. These would be the B protons. In terms of C and D, these two protons are closer to the oxygen, so those are probably the most deshielded. So I'll put the D there, and I'll put the C here. Let's go down and take a look at the carbon and see if it's consistent with this structure. I'm going to redraw it right here. So let me redraw the compound. There's my methyl group. There's my oxygen. You see that we have 1, 2, 3, 4, 5 signals in here. It actually says there's 2 here. Oops, I didn't even notice that until just now. So it says there's 2 unresolved lines here. That means they're overlapping, so D and E. And then we have F up here. All right. Well, we have a total of 1, 2, 3, 4, 5 signals. So we have a total of 1, 2, 3, 4, 5, 6. Yeah. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm just checking to make sure this makes sense. Well, if we draw this compound with the methyl pointing down like this, you can clearly see that there is a plane of symmetry running through the molecule like this. We've got 1, 2, 3, 4, 5, 6 types of carbons in the molecule. 6 types of carbons in there, and we have 1, 2, 3, 4, 5, 6 signals. So makes sense. Well, A is going to be the most shielded carbon in there. So I would say that's going to be the methyl group that's not going to be attached to the oxygen. So this would be the A carbon. Then we have the methyl group that's going to be attached to the oxygen. So this would be B. For C, D, E, and F, C, D, E, and F, I would say that F and E would probably be these ones. I wouldn't be all that picky. I'd say F and E, because it's so small. And when they're so small, it usually means they don't have a hydrogen attached to them. And I'm assuming that when it says there's another line in here, I'm assuming it's something really, really tiny. So I'm assuming that, E is buried under here. So which one is F and which one is E? I'm not 100% sure. So then C would be the ones that are closest to the oxygen. And then D would be the ones that are further away from it. D would be the ones that are, D would be the ones closest to the oxygen because those are the most deshielded, and C would be further away from it, like that. So just like that, we were able to annotate all of the carbons on the molecule. And sometimes you'll end up with an ambiguous situation like this where you're not really 100% sure. If I had to guess, I would say that the one that's closer to the oxygen is F, and then the one that's further from the oxygen would be E. That makes the most sense. Like that. So there you go. We were able to determine the structure of the molecule, and we were able to annotate the carbon spectrum, the Proton Nmr spectrum, and the infrared spectrum. So that covers all the practice problems that we had in there.